Welcome here to the final day. Here we go. We are talking about carbohydrates, which is 13, I think so. So last time we talked about carbohydrates. They are obviously compounds that contain carbon, hydrogen, and oxygen. They are sometimes referred to as sugars. As we talked about, there's a couple of things. We talked about chiral carbons, and a chiral carbon is really a carbon that has 4 different groups basically attached to it, and that would be a chiral carbon. A chiral carbon is, if you put it in front of a mirror, its mirror image will not superimpose, so the mirror image will not superimpose. And that's different than, say, a achiral carbon or molecule. An achiral molecule has really not 4 different groups attached. They have, obviously, in this case, for example, a couple groups that are the same, and that would make it achiral. And because of that, what that means is you can't take the mirror image, you could take it out, you could rotate it, and it will fit over the original guy. So the mirror image will superimpose. We also talked about the idea of when we draw carbohydrates, a lot of times it's sort of almost like a line structure. So where the kind of lines intersect are carbons. We also talked about that at the last chiral carbon from the most oxidized group. If the OH there is on the right-hand side, that was sometimes referred to as the D sort of isomer. And if you look at the last chiral carbon and the OH group there is on the left-hand side, that is the L isomer. And remember that a compound or a carbohydrate can have more than one chiral carbon. So it can have a number of different chiral carbons. It can also have some achiral carbons in there as well. I think we finished up talking about that really carbohydrates and these sort of monosaccharides, which are individual sort of sugar units, they really do have 2 sort of organic groups up on the top of them. They typically will have either the aldehyde group, like we see in organic chemistry, or they will have really a ketone type group on them. And in sort of the carbohydrate sort of arena, if it does have the aldehyde group, those are what are sometimes referred to as an aldose because it has the aldehyde group. If it has sort of the ketone group here, those guys are what are referred to as a ketose because it has a ketone group on it. We also can classify a carbohydrate by the number of carbons that are present. So you could count the carbons like 1, 2, 3, 4, and 5. That would be a pentose. You could have like a hexose, a tetrose, which would be 4 carbons. So we can kind of arrange them that way. Just like in organic chemistry, if it does have the aldehyde group, it will always be at the very end like this. And just like in organic chemistry, if it's the ketone group, it will never be at the end. So, you'll have something like this, perhaps, and something like this without the extra line on that side there. So it typically will have a carbon double bond there and something like this, and then something like that. So usually the ketone group will look very similar to what you see in organic chemistry. It'll be towards the end, but the double bond will be one inside of the ending carbon. Any questions on that there? For the most part, we also talked about most carbohydrates have this guy here at the end. And I won't say 100% of the time, but most of the time, your very last chiral carbon is a lot of times the guy right above that guy. But it won't always be the case, but that's very common. Any questions on any of that stuff we talked about last time? All right. So as I mentioned, I think we looked at the aldose last time. This again is the ketose carbohydrate, and this is our ketone group. Remember, again, our ketone group is a 3-carbon run with the double bond happening there. So right there is basically our ketone group, just like we find it in organic chemistry. And again, you see that the carbon-oxygen double bond is in from the end. And once again, you can classify this monosaccharide in addition to a ketose, because it has a ketone group, based on the number of carbons. So once again, this has 1, 2, 3, 4, 5, and 6 carbons. So this would be a hexose. So that's why it's sometimes referred to as a ketohexose. Keto because it has a ketone group, hexose because it has basically 6 carbons. Much like in organic chemistry, when we number the carbons, we always number from kind of the functional group. It works the same way here with carbohydrates. So if we were to number these carbons, let's do this screen. This carbon here would be carbon 1. This here would be carbon 2. That would be carbon 3. That would be carbon 4. That would be carbon 5. And that would be carbon 6. And just like if we had a aldose up on top. And if we wanted to number the carbons, we would once again start with the oxidized group, or the carbohydrate, or the organic group, which would be 1. This intersection here would be 2. This would be carbon 3. This would be carbon 4. That would be carbon 5. And that would be carbon 6. So again, we really do sort of number the same way as we do in organic chemistry. That functional group really sort of takes the priority and is always sort of at the top. And that's important because, once again, when you're looking for like DRL, we're looking for the last chirocarbon furthest away from that functional group and which side that OH is on. So in this case, that would be like a D sort of function there. Any questions on that there? All right, so let's take a look at each of these. We want to know, are they an aldo or keto, and is it a tetrose, pentose, or hexose? So take a moment and see what you come up with here. So this would be a hexose. So this would be an aldohexose, meaning it has an aldehyde group and 6 carbons. Looking at the guy here on the right, there's our 3 run of carbon with the double bond, which is not at the end. So right off the bat, that should tell you it is a keto because it has the ketone group. And if we count our carbons here, we got 1, 2, 3, 4, and 5 carbons. So 5 is like pentane or penta, and this would be a pentose. So this is a keto pentose. Again, a keto, it has a ketone group. Pentose, it has 5 carbons in it. Any questions on either of those there? Okay. All right. So let's talk a little bit about the structures of these carbohydrates. As I mentioned before, it is very common that these guys are drawn almost like line structure. And once again, everywhere it sort of crosses, again, they are carbons and they're not usually written a lot of times. The other thing that sometimes is left off are the hydrogens, but you know, if there's an OH on one side, there should be a hydrogen on the other side, always. So this is glyceraldehyde. It has 1 carbon, 2 carbons, and 3 carbons. So it is a triose, right? Because it has 3 carbons. It is also an aldose because it has the aldehyde group. And in this particular case, this carbon right here, I'll just color it in, is the chirocarbon here. It's the only chirocarbon it is. Once again, you can see it's kind of right above that. And here we do see our OH group on the left-hand side, which is why that is L. Opposite is true here. This would be our chirocarbon right there. OH group there is on the right-hand side, so that is why it's a D. And again, this is the last chiral carbon. So when you are looking to determine D and L, like we talked about, we were looking for the last chiral carbon furthest away from the double bond, basically. And that's where you make your determination. So again, as we saw last time, you could have multiple chiral carbons, but if you're trying to determine D or L, you want the furthest one down from the bottom. That is the last chiral carbon to make that determination from. As we see here, our D and our L. Here's a couple of compounds here. This is glucose and ribose and galactose. Put a little star on this page. You do need to know these structures, yes, not to draw, but to recognize, yes. So you should know what glucose looks like. You should know what ribose looks like. You should know what galactose looks like. Again, you won't be asked to draw them from your head, but if you have some of these pictures, you need to be able to maybe recognize them as these guys. Glucose here is an aldehyde. So it's an aldose. It also has 6 carbons, 1, 2, 3, 4, 5, and 6. This again is D-glucose because that is the furthest chiral carbon. How many chiral carbons does glucose have, by the way? It has 4. That would be chiral. That would be chiral. That would be chiral. That would be chiral. So all 4 of those are chiral carbons. Again, the furthest one down the road is where we look at for our OH there. Once again, this carbon here has this group, and this group, and everything on the bottom, which is 4 different groups. And then you kind of move everything down. They all have chiral carbons. This guy at the very bottom is not chiral because it has 2 hydrogens, right? So that eliminates the possibility of 4 different things being attached to it, but it does have 4 chiral carbons. This is ribose, which is also an aldehyde. It actually only has 1, 2, 3, 4, 5 carbons. So it's got 5 carbons there. Again, carbon number 1 would be up here, and carbon number 5 would be the guy on the bottom in terms of numbering. Again, it would have actually 1, 2, and 3 chiral carbons, which again, the OH here is on the right-hand side, so that's D. This is galactose, which again has an aldehyde, 1, 2, 3, 4, and 5, 6 carbons. And each of these are chiral. So that's a chiral carbon, chiral carbon, chiral, and chiral carbon there. It has 4 different ones. Again, the OH here being on our left. So you do need to be able to recognize these structures if they happen to be given to you as to what they are. All right, so for each of these, are we D or L on these guys? This is chiral. That is chiral. Once again, this would be the furthest chiral carbon from the double bond. And that one also is on the left-hand side, so that would be L. And coming down here, we would have chiral, chiral, and chiral. Once again, this is the furthest one there from the double bond. And that would be on the right-hand side, which would be, I was going to write R, but D would probably be a better one there in that case. Now, you may be wondering, how did I figure out if those are chiral that quickly? Really, the simple way is if they're drawn like this, and this guy are different, it's going to be chiral. As long as this guy and this guy are different, it's going to be chiral. And as long as this guy and this guy are different, it's going to be chiral. For all the kind of carbons in the middle, not from the top or the bottom, but everything's sandwiched in the middle. If the left and the right-hand side guy are different, it's going to be a chiral carbon. If they're same, or you got 2 hydrogens on one of them, it wouldn't be an achiral. So that's how you can kind of quickly just kind of go through it and go, okay, chiral, chiral, and not chiral. Any questions on that there? All right. Hopefully they agree. That would be better. I would say that's good. All right. So let's talk a little bit about glucose a little bit more. As I mentioned, you do need to be able to recognize glucose. It's found in fruits, corn, syrup, and honey. It is a form of C6H12O6. It's known as blood sugar, right? We take glucose in through eating, goes through a little glycolysis, right? We use it for some energy. We store unused ones, right, in our body. that we could further break down through gluconeogenesis if we have to break it back down going the other way. It is also the monosaccharide polymer of a lot of things like starch, cellulose, and glycogen. We'll see that at the end of this chapter. Pretty much putting a bunch of glucose molecules together makes things like starch and glycogen, which is our stored energy that we break down through gluconeogenesis when you don't have any sugar coming into your body. Also, blood glucose levels are important. If you don't have sort of a normal range for your blood glucose, if you have sort of a higher level of blood glucose, that is what's known as hyperglycemic. Hyper meaning more than, kind of like we talked about hypotonic. If you have less than sort of a normal range, that is known as hypoglycemic, which means you're a little short on some of your blood sugar along the way. Right. You test your blood sugar through a blood test, right? Good idea to fast before you do that, right? Not have something to eat right before you take that. Otherwise, your glucose levels are going to be all off the base and stuff like that. Unless you're trying to hide something, then you eat something and go, oh, I was just eating. That's why it's really high, and stuff like that. I had a sugar donut right before I took my test. It's all right. So fructose is another one that you do need to recognize as well. So again, you won't be asked perhaps to draw it, but if the structure shows up, you do need to be able to sort of recognize it. It is a ketone, so it's a ketose, fructose. So it has the ketone group there. It also is 6 carbons, so same sort of formula as glucose. It's the sweetest carbohydrate. It's found in fruit juices and honey. In the body, it will convert into glucose. So fructose, you do also need to kind of recognize the structure there. So put a little star probably there just in case for the final. Galactose. Also, another 6 carbon sugar. It's not found in free nature. It's actually obtained from lactose, which is a disaccharide, and putting 2 monosaccharides together. It's very similar to structure to glucose, except at carbon number 4, which would be 1, 2, 3, and 4, with the OH there. Number 4 is a little bit different than what you see in glucose. Since you're not asked to draw it, you don't have to worry about drawing it, but we'll take a look at the structure there. All right. So let's talk a little bit, though, about the cyclic structures of carbohydrates. So in sort of that straight chain form, sugars can exist, but they oftentimes will sort of close up on each other and make like a cyclic compound, very much like what you see in organic chemistry. And really, when they sort of close in on each other, they pretty much will make 2 types of rings. They'll make a ring like we see here, which is very similar to the cyclohexane ring. It's basically a 6 carbon ring, but it's really not, because there's an oxygen in there. It's actually a 5 carbon ring with 1 carbon there, 2 carbon there, 3 carbon there, 4 carbon there, and 5. And it's obviously based off of cyclohexane, but it does have the oxygen that gets inserted there, rather than that kind of 6 carbon that you typically see. The other type of cyclic sort of structure that the sugars will sort of make themselves into is like cyclopentane, which is sort of like a 5-member ring. Once again, though, it's actually not 5 carbons, because it will have a oxygen also inserted into the ring, but it will still have 4 carbons really in this case. And one of these 2 rings are typically the ones that you would draw if you needed to kind of convert it from the straight chain into the cyclic structure. We're going to talk about how to do that. And there's those 2 prettier drawn pictures than what I drew there. But typically what happens in a lot of cases is these are typically the ones that we see for monosaccharides with 5 to 6 carbon. And in a lot of cases, it is usually carbon number 5 on the chain that actually goes and finds the double bonded carbon and oxygen. So if you have an aldehyde type topper, if you will, coming down here, like carbon number 5, that is usually the one that will go and sort of attack the carbon there. If you have more of a ketone topper, if you will, on your carbohydrate, again, coming down to, we'll go here, carbon number 5, it will go over here to the carbon-oxygen double bond. So when these guys basically close in on each other and make a cyclic structure, always the carbon-oxygen double bond as to where it comes in and actually closes up the ring. That's also in that process, as it's kind of closing up the ring, how really the oxygens get inserted into the ring as part of that sort of structure as they come together. So, a stable cyclic hemiacetals, and if you remember, a hemiacetal is really a carbon that has an OH group attached to it, also has an oxygen carbon type group attached to it. So when the carbon oxygen double bond and the OH are part of the same molecule, for hexoses, the hydroxyl group on the carbon, the 5th carbon, reacts with that double bond. And again, we get the sort of structure that is like for the D isomer, we will always get the last sort of group that's usually achiral will always end up above the ring. So in either of those ring structures, that ring structure or this one, we will always end up with this guy up on top. And for reference point, that guy is basically this group here at the very bottom. So this group at the very bottom is always like carbon number 6 for the most part in hexoses. That should be carbon number 6. So number 6 carbon and hexoses will always end up above the ring there to the left in that position. That's important because we will actually number the ring based off of that guy's number. So if that guy is carbon number 6, when we go to the ring, that would be carbon number 5. And then we actually go counterclockwise. That would be carbon 4, 3, 2, and 1. So that is how we would sort of number that ring. Same thing with the guy above here. This would be carbon 6. This would be carbon 5. That would be carbon 4. That would be carbon 3. That would be carbon 2. And carbon number 1 will be off of the ring. Either there or there will be actually off of the ring on that one. So in a hexose situation, we always put kind of carbon number 6 up on top, come to the ring, carbon number 5, go counterclockwise in terms of our numbering. Any questions on that there? So let's talk about, how we do this. I'll just draw one here. Why not? We'll just make one up here. Let's just say we wanted to take this guy and we wanted to, we'll just make some up here. We'll go OH there. We'll do a little OH action over there, a little OH action over there. We're doing OH over here. Okay, so if we wanted to kind of turn this guy into a cyclic structure, what we would want to do, frankly, is first off, kind of count the carbons. Is one easy way to do it. So we would go with 1, 2, 3, 4, 5, and 6. And basically what we would actually do is we're just going to take the whole thing and basically just drop it on its side. So we're just going to take this whole thing and like it fell over, let it drop down. So if I let it fall over and fall on its side, I'm going to redraw it. And basically, if it does fall on its side, everybody on the right-hand side here will end up down. And everybody on the left-hand side here will end up up, right? So if you took something and just dropped it down, everybody on the left goes up, everybody on the right goes down. So that means if this is carbon number 1, my carbon number 2 here would mean I have my OH here and my H here. My carbon number 3 here, I would have then my H and my OH. Carbon number 4 here, I would have my H and OH. Carbon number 5 here, I would have my OH and my H. And then I would have my CH2OH happening there, which is obviously this group right here. First off, any questions on dropping it down there? All right. Now, the hectose, what that means is it is always going to be really the last chirocarbon, or carbon number 5, but it will be usually the last chirocarbon. It's going to go and find the double bonded oxygen. And this is really going to tell us how many carbons we actually need in our ring structure. So when I close this guy up, I have 1 carbon, I have 2 carbons, I have 3 carbons, I have 4 carbons, and I have 5 carbons that's going to become a ring. Now, we saw those rings a second ago. The one that had 5 carbons is the one that looks like cyclohexane, but it does have the oxygen inserted in there. Now, what we see is, excuse me, outside of the ring, we have this 6 carbon, right? So this is carbon number 6. And as we know, that 6 carbon always goes right there, upper left of the oxygen. We now can number our ring. And if we number our ring, again, this is going to be carbon 6. This is going to be carbon 5. That would be carbon 4. That would be carbon 3, if I could count. That would be carbon 2. And that would be carbon 1 there. So now we're actually ready to just build the rest of the structure. And it's pretty much laid out for me. I am going to always skip carbon number 5 or wherever carbon came in to close the ring, because that's like all over here. Basically, all that action right there is carbon number 5 and 1 coming together, all this sort of action coming around that corner. So then we're going to go to carbon number 4. And frankly, I see my OH group is up. So I go to carbon number 4, I draw a line, and I write my OH up. I go to carbon number 3, I see my OH is also up. I go to carbon number 3, I draw a line, I put my OH up. Go to carbon number 2, my OH is down, which means I go to carbon number 2, draw my OH down. By the way, on the other side of that line is a hydrogen. It's usually not put into these type of structures, but on the other side of the line is basically hydrogen. That's all my hydrogens, all my carbons. I still have carbon number 1. So carbon number 1 depends on whether or not you're asked to draw the alpha or the beta anomer. Alpha is what that means is if you're drawing the, say, alpha one, you would do the OH group down. If you're the beta one, you would go up and draw it on the other way. So they'll usually tell you to draw the alpha or draw the beta one. And that is what happens here on our last carbon. Any questions on that there? Okay. So take a look at this one more time. We'll take a look at one here. So we have our guy here. Once again, we're just going to drop it down. Or you can remember right goes down and left goes up. You don't have to drop it on the side. You can do that as well. Once again, we're going to take this guy and close it in. And that is going to give us 1, 2, 3, 4, and 5 carbon type rings. So that is what they should have going on over here. Again, our number 6 carbon goes here. And then we go counterclockwise in terms of the numbering of our carbons. And in this case, we have our OH group there on the bottom on number 1. And again, if you look back here, we have OH basically down, up, down is sort of the arrangement that we have there. So that's what we should see here on the ring. We should see down, up, down, basically. So again, it follows that same route. And again, like I said, if you're asked to draw the alpha, you would put that last OH group on the bottom. And if you were asked to draw the beta anomer, you would do the last OH there up on top. Questions on that? All right. Well, I did one. Let's try you do one here. I'll go back here. All right. So you draw this guy here. Let's do this. And let's just make up some stuff here. We'll go this way. We'll go this way. We'll go this way. We'll go that way. Why don't you draw the beta anomer? Then why don't you also do this one as well? Let's do and let's do the alpha for this one. All right. So draw the cyclic structure for the beta up on top and the alpha one for the guy on the bottom. See what you come up with. I just made it up, so hopefully we'll hope for the best. And our fake sugars, we'll just draw those guys. We know that it's going to be here carbon 5 in this hexose, which is our last chirocarbon. It's going to go up and basically attack our carbon number 1. That means that, frankly, if I just count the carbons that will encompass that, I know how much of a ring I should draw. That's 1, 2, 3, 4, and 5 carbons, which means really I should draw my kind of 6 carbon ring here, like cyclohexane. I could drop it on its side, or again, I can remember that when I do drop it on its side, everybody here on the right is going to go down, right? And everybody here on the left will go up, basically, when I drop it. We do know that this guy here is left off of the ring, and that guy will always end up here to the left of the oxygen. And that gives us a reference point that that is carbon 6, which means that is 5, 4, 3, 2, and 1 coming counterclockwise. So once again here, I'm going to go to my structure on the left. I am going to skip really the carbon that came together to make the ring, so I'm not going to really worry about those carbons. So what I have left is the guys in the middle. Starting at carbon number 4, my OH is on the right, which means when I drop it, it will go down. So I would draw a line down with the OH. My OH here is also on the right, which means it should drop down a carbon 3 and a carbon number 2 also to the right, which means it should drop down here. The last OH here would be determined by us drawing the beta, and beta means that we would throw the last OH up. One there. All right, so looking at the bottom one here, we'll kind of take the same approach. It's going to be carbon number 1 here, carbon number 2, carbon number 3, carbon number 4, carbon number 5, and carbon number 6. So once again, it is 6 carbons. We're going to take our last chirocarbon, which is this guy. Remember that it is always going to go to the double bonded carbon. So in this case, it's actually not carbon number 1, but it is carbon number 2 as to where that is going to go. That means part of the ring here would be 1 carbon, 2 carbons, 3 carbons, and 4 carbons. So really, we're going to draw the 5 cyclopentane type ring with our oxygen in the middle. Everybody see the difference there? We went to carbon number 2 versus carbon number 1 means our ring is 1 less carbon and should only actually have 4 carbons on the ring. Any questions on that there? At this point, what we actually could see here is a couple of things. We see that this group is not part of the ring, and we see that this group is not part of the ring either. But just like the other one, we do know that carbon number 6 will end up over here. So we do know that that's carbon number 6. That means that this would be carbon number 5, carbon number 4, carbon number 3, and carbon number 2 in this case. Any questions so far? We're going to do our same approach. Yeah. What is the 6? That's just the number of the carbon. It's not really part of it. That's carbon number 6. Why does the top one have the 6 carbon shape? It's because so on the top one we started at this carbon here, right? And that's what closed into this carbon right here. So if we count basically all the carbons, including the 2 that came together, this would be 1 carbon, that would be 2 carbons, that would be 3 carbons, 4 carbons, and 5 carbons. So all those are all part of the ring. Now, when we come over here, this is the carbon that's going to go and close in on this carbon. So when we count up the carbons, this would be carbon 1, that would be carbon 2, carbon 3, and carbon 4 would be the first one there on the bottom. And those are the 4 that really make up the ring. That's how we get all our proper number of carbons. So it's kind of like the 4 carbons is like the cyclopentane ring, even though it has the oxygen. And obviously the 5 carbons like the cyclohexane ring, but it has the oxygen. And the oxygen is inserted there as those guys kind of close in on each other and come together. The oxygen kind of gets incorporated into the ring instead of another carbon. Other questions on that? All right, so we're going to do our same thing here. We're not going to worry about the carbon that made the ring on either side. So that leaves really just these carbons here. I'm going to do my same thing. On the right-hand side, it's going to be down, right? And up, left-hand side will be up. So we would actually start here at carbon number 4, which I keep scribbling, is about there. And carbon number 4, our OH group is on the right-hand side, which means it should go down. At carbon number 3, which would be this carbon right there, it is on the left-hand side, which means when it falls over, it'll go up. So it will go up. My last OH is based on alpha, which means the last OH should go down. But now on this particular one, if we look at our ring, we ended at carbon number 2, right? But we still have carbon number 1. So at the other end of this guy is where carbon number 1 will end up. Right there, carbon number 1. So it will end up out of the ring because as it closed in, those 2 parts were basically left off of the ring. And those are the group here that was left off of the ring and this that was left off of the ring. And we have, that's different than over here on the top one. This is the only one that's left off of the ring, which is what we see happening here. This case, the CH2OH went up on top because alpha told us the OH had to go on the bottom. If we did beta, we would just flip it. The OH would go on top, the CH2OH would go on the bottom. So if you had to do the beta one. Questions on that there? Fun with rings. It's good stuff. All right. So just looking at these rings, let's see here. There we go. The formation of a cyclic hemiacetal, as I mentioned. So this is like carbon number 5 coming in, and you can see it's actually the OH group that's on carbon number 5 where that oxygen comes from that gets inserted into the ring. So that is where basically the oxygen comes in as those 2 guys are closing. The hydrogen actually takes a hike over to here and makes the OH group. And this is our hemiacetal, if you remember. That is our carbon that has an OH group, a hydrogen, and an oxygen carbon group, basically. So that is your hemiacetal right about there. The oxygen gets inserted into the ring. It's that OH group as it's closing in. It gets inserted. The hydrogen actually leaps over to the double bonded oxygen and makes an OH group over there. And again, that's how, you know, it kind of becomes that sort of carbon. Now, in terms of glucose, it will sort of spend time between alpha and beta, with most of the time hanging out there, the beta sort of formation there where the OH group is up, Once again, alpha means the OH group there is down. Here is fructose. It's kind of like the one we just did. Because it is a ketone, that guy here is going to have to find that second carbon. And again, that is why we have kind of the smaller ring that we end up with. Once again, 1 carbon, 2 carbons, 3 carbons, 4 carbons in the ring, which is our 4 carbons basically right there. So you usually will get this type if you're doing a ketone type, a ketose type of closing in on the structure. You can't get it with an aldehyde if it's like a 5 carbon instead of a 6 carbon carbohydrate, because it's missing that 1 extra carbon when it does close in. You can end up with this sort of structure for an aldose, but a lot of times you'll see it with a ketose because it's going to carbon number 2. But something like ribose, for example, or something like that, where it's kind of has 5 carbons only, because it's missing that extra carbon, it will close in only on a 4 sort of member ring. All right, so we'll talk about something like this, which is what happens if we wanted to kind of go backwards from like the ring to this structure here. I don't know why you would want to do that, but maybe you'd want to do that. Maybe, well, I feel like I just started saying it, so I feel like I should finish the sentence. Let's just say we wanted to draw this thing as a as a D-galactose. I like the enthusiasm. It's nice. It's very nice. It's just some there's some goodness there. All right. So the first thing you would want to do is perhaps count carbons to know what you're drawing. So we got a 1 carbon there, right? We got a carbon there is 2, 3, 4, 5, and 6. So we do know it's going to be a 6 carbon straight chain if you happen to want to draw that. We also know that I do not see anything over here, and I only see something over here. That tells me that it really is a aldose up on top. So as you just saw when we drew a ketose, we ended up with a different ring, right? And some carbons off both sides. So since there's really nothing there, I could probably safely know that I should have probably this group up on top. I also should safely know I could do 6 carbons total. So that's 1, 2, 3, 4, 5, and 6, which would be here. And I always know that this group over here is carbon number 6, right? Which means that this would be 5, 4, 3, 2, 1. Just like we number it to draw it, we can number it the same way. Why is that helpful? We're going to basically just work it reverse. We're going to skip. So this would be carbon 1, this would be carbon 2, this would be carbon 3, this would be carbon 4, this would be carbon 5, and that would be carbon 6. We're going to skip carbon 5 like we did when we put it together. So we're just going to go carbon number 4. And I see my OH group is up, which means if it's up, it's on the left side or the right side. It's on the left side, right? So I go to carbon number 4, I put an OH, and on the other side should be a H. I go to carbon number 3, I see my OH group is up, which once again means it should be on the left-hand side. And that would give me an H. I go to carbon number 2 there, and I see my OH group is down, which means it should be on the right-hand side, right, as it's dropped. Entire thing built at this point. That is why this is important, because D means the OH group is on the left or right. Right. So that would be my last chirocarbon, which would be there. And now I just built it. Even though you didn't want to, we did it anyways. So you can't go backwards. You just kind of work your way backwards. Again, if you had something where you see I can just make it up here. And then we should have 1, 2, 3, 4. And I shouldn't have that OH there. I got a little happy with the OHs. There we go. There you go. So once again, if you had something like this that we drew earlier, you could really look at, like I said, you could count the carbons, which would be 1, 2, 3, 4, 5, and 6. So once again, you would know it would be a 6, but in this case, we have this group and this group that's off of it. So that would tell you that it is a ketone. So that's the difference and sort of what you would be looking for if you kind of went backwards. Enough of that nonsense. Nobody wants to go backwards. So let's go forward, shall we? Let's talk about some of the properties of these monosaccharides here. All monosaccharides with a carbonyl group. A reminder that the carbonyl group is the carbon double bond. They oxidize to give a carboxylic acid, and that means that they are reducing sugars, so they will be oxidized. They will undergo a reaction with Benedict's reagent to give the carboxylic acid, just like in organic chemistry, right? We use Benedict's reagent to determine the oxidation of a aldehyde to basically a carboxylic acid, right? By inserting the oxygen in there. They include all pretty much monosaccharides, glucose, galactose, fructose, all those guys that have that will have the ability to kind of go through step. So they are pretty much known as reducing sugars. When they do get reduced, here's that process there. Just like in organic chemistry, pretty much everything stays the same, except that we basically put an O there. And that's our same idea as our alcohol to aldehyde to carboxylic acid oxidation that we talked about in organic chemistry as well. That is our Benedict's reagent going from blue to yucky red or orange as well. Reduction of monosaccharides. They're sometimes called aldehdols or sugar alcohols. We're not going to worry too much about that. So I want to, I just did. I swiped that way. I'm skipping it. Yeah, I'm still skipping it. By the way, that is our carboxylic acid, that's our aldehyde, and that's our alcohol. Yeah, so very much the exact same things, but we saw from our primary alcohol to our aldehyde to our ketone. Now I'm skipping it. Let's talk a little bit of disaccharides, talk about some cheese, a little bit of milk, or not if you don't like those things, I suppose. So disaccharides are two monosaccharides together. They're put together by basically taking out water. So basically squeeze out water, put them together, and you got a disaccharide. You do need to know these, yes? So you do need to know that maltose is made up of 2 glucose units. You need to know that lactose is made up of a galactose and a glucose. And you do need to know that sucrose is made up of fructose and glucose. So put a little starry on that. We're going to go through each of these here right now individually, but you do need to know these guys. So let's talk about maltose first. It is malt sugar. It is composed of basically 2 D-glucose molecules that are together. And they're also held together by what is referred to as a alpha 1,4 glycosidic bond. And we'll take a look at that bond in just a second, but that is what holds maltose together. Again, it's basically achieved by basically taking water and sticking the 2 glucose molecules together. The reason it's called an alpha 1,4 bond is because it's the OH on carbon number 1 and the OH on carbon number 4. Basically is where that bond comes from. That's what the numbering refers to, 1 and 4. And alpha because it's coming down, as we will see here in a second. Uses cereals, candy, and brewing, and it also comes in both the alpha and beta form. So let's take a look at it. This is carbon number 1 on one glucose. This is carbon number 4 on another. These guys come together. These are both alpha, and it makes this alpha 1,4 glycosidic bond. 1 because it's carbon 1 in this guy, and 4 because it's carbon number 4 on the other glucose molecule. The way you can remember it's alpha 1,4 is it will always look like this, like it's coming down, like alpha means down, right? So it's like coming down in that sort of form to bond it together. This is the alpha anomer because at carbon number 1 of this glucose, the OH is down. So just like the OH there is down. So 1,4, one on one glucose, 4 on the other come together, make this alpha 1,4 glycosidic bond. And that is what makes maltose 2 glucose units. Obviously, if you want to break it apart, you throw water in there and you get both of the glucose units back together, or separated out, I guess is a better way of saying that. Lactose is our disaccharide, is made up of galactose and glucose. It is held together by a different type of bond. It is what is referred to as a beta 1,4 bond. And that is because it is the beta guy here. And that's at carbon number 1 coming to carbon number 4. And they're coming together. How do you remember that? Beta means up. The bond will always look like it is going upwards. And that upwards direction is a good way to remember that, as opposed to our alpha, which looks like it's coming down, right? So that is alpha, beta coming up here, making our beta 1,4 bond here. People have trouble breaking perhaps that bond for lactose intolerance. We have that OH group on the bottom there, which would make it an alpha. So once again, you do need to know lactose is made up of galactose and glucose and held together by a beta 1,4 bond, glycosidic bond. Sucrose, which is our sugar, excuse me, is obtained from glucose and fructose coming together. It is actually coming together through an alpha beta, like the old supermarket, 1,2 glycosidic bond. Nobody knows what I'm talking about. No. Alpha beta, anyone? Yes. All right. Still not. You still use that. One person knows in the room. That's good. Actually, I'll just stand there and go alpha beta. All right. It was like then became like food for less, and then it's like Ralph's. That's all right. I digress here. So putting these guys together, this is going to make a alpha beta 1,2 glycosidic bond, and that's because it is the alpha guy in carbon number 1 and the beta guy in carbon number 2, and this one goes straight down basically, and that has both of them. It's alpha going down and beta kind of coming up, and that is what the alpha beta 1,2 glycosidic bond looks like. Yeah. All right, we'll talk about other stores later. All right, so if we wanted to break these guys apart, our disaccharide, we want to just basically throw in water, and basically it would break apart through the bond, and you would get back your 2 individual monosaccharide units, which in this case would be glucose and fructose. Sweeteners, nobody has time for sweeteners. All right, so for each of these, we have lactose, which is made up of like lactose and glucose. Maltose is a couple of glucoses, right? It's sucrose. Or the glucose here. So you do need to know pretty much the slide. Yeah, that's a good slide to know, right? Those guys will make it up. All right. You should also know the glycosidic bonds, what they look like. Again, you may not be asked to draw them, but you need to be able to kind of recognize them if you see them in a picture. All right. We'll talk a little bit about polysaccharides. Polysaccharides are long groups of pretty much glucose molecules together where we take out water and they just kind of connect up. So very, very long chains of glucose molecules. That is what polymers are. They include amyloase and amylopectin, starches that are basically made up of our alpha D glucoses. Our potatoes are good. They also include glycogen. Again, that's sort of what we store a lot of our sugar as in our body and our muscles. Again, we could kind of call it out if we need it for some energy, so you don't have to use ketones or anything like that to survive on, which is made of alpha D glucose. They also include cellulose, which is plant and wood glucose. So let's take a look at each of these. There's our potato. And part of our potato is amylose. And amylose is a bunch of glucose molecules together. and we look at the bonding between these molecules, and we see one that looks like this. This tells us it is a alpha, yes, and it is a 1 to 4 glycosidic bond by the way that it looks. So amylose is a bunch of glucoses. The key of this guy is they are all straight in a row. No branching or anything like that, just a long straight chain of those glucose molecules together, all held together by the alpha 1,4 glycosidic bond. Amylopectin, which is the other part of our potato, is basically the same thing. It has the long chain of glucoses that are held together by the alpha 1,4 bond. But every so often, we have a branch that occurs there. So that is the difference there. There's a little bit of branching that happens between alpha 1,6 bond. So that's the alpha 1 and carbon number 6 of the other. So that branching occurs. This is carbon 6 of one glucose, and carbon number 1 of the other. And that branching actually occurs between those two guys. So that is why it's a 1,6 that occurs. That allows it to basically branch up, right, to the glucose above it, because it's attaching to number 6, as opposed to just keep attaching along the way there to number 4. So they're both held together by alpha 1,4, but amylopectin also has more branching that occurs, and also is held together at the branch points by an alpha 1,6 bond that occurs. As you can see there, these are just a bunch of straight chains and a lot of branching and curling that's happening there with our amylopectin. So amylose is linked together, like I said, by that 1,4 glycosidic bond. It is continuous, it is unbranched. And again, our amylopectin also has the base of it is that straight chain. But again, as every so often, it has a branch point where it can again run another chain that happens. And again, to kind of stack them, we get the branch point that happens between carbon 1 and carbon 6 of opposite glucoses. You can just kind of think of it like 1 is at the end and 6 is up on top. So that is how we get the kind of branch part that occurs between those two guys. Is a polysaccharide that stores alpha D glucose in muscle. It is similar to amylopectin, which means it has the straight chain and also the branching, but a lot more branching points basically happening to kind of curl everything together. So there's a lot more branching that occurs in glycogen. Cellulose, on the other hand, is a polysaccharide of glucose units. It has the beta 1,4. So once again, if you look at this linkage, it is that linkage that we talked about, this kind of going up like a beta. So again, that is how you could kind of recognize it, different than an alpha one. And it is between carbon number 1 here and carbon number 4 on that one. So again, if you just kind of draw your rings and number your rings, that is 5, 4, 3. I drew the wrong ring there. It'd be better if you draw the right ring there. That would be good. Lost me a carbon along the way there. 5, 4, there you go. 3, 2, and 1. So if they kind of go side to side, it's always going to be like a 1,4 connection that's going to happen. And again, in this case, it is a 1,4 connection, but we see it kind of going upwards, which tells us it's a beta, as opposed to that 1,4 connection where it's kind of going downward, which is an alpha connection. Humans cannot digest that bond and break that bond down, so you probably shouldn't, maybe eat that cotton or anything like that. Would probably be a bad idea. All right, so taking a look at these guys, the polysaccharides and the type of bonds that are happening here. As we saw, we had our cellulose, which has the beta 1,4 bond. We have our amylose, which has just the alpha 1,4 and it's straight across, no branching. Amylopectin, alpha 1,4 and alpha 1,6 with branching, which is the 1,6 part of it. And our glycogen, also the exact same bonds, but a lot more branching that is occurring.